Hi there, welcome to Professor 3. In today's video, I will show you how to do plane strain, plane stress simulations, and also if you can transform a 3D simulation that you see on the screen right now to a plane strain or plane stress case. Okay guys, let's jump into it and see how we can replicate plane strain, plane stress simulation, and then a 3D simulation, and then how I can convert a 3D simulation into a plane strain condition. So again, I will go with the fictitious part. Let's go with the 2D planar first. I'll make a square of 1 by 1. Okay, it's all millimeters. So this is how it looks like. Then I go to the properties. I will create a material property, elasticity. Let's use a value of 110 megapascals, 1000 megapascals. 0.33 is this, and we can try some plasticity as well. So let's give a yield strength of 350 at 0.0, and then we give it an ideally plastic material, so it will be like a horizontal line in a stress strain curve after the plastic region has started. So now I will create a solid section, genius, and you can specify plane strain or plane stress thickness. I'm giving a thickness of 1. You can use whatever thickness you have in your component. Next, I will assign this section to this. Done. Now I will go to assembly, assemble part, step, create general static step, total time 1. Let's make energy on. Maximum number of increments to be 10,000. Initial time increment to be 0.1 and the maximum to be 0.1, so that we can have 10 increments for the total time period of 1. Then I move to there is no interaction, so we directly go to the loading condition. And in this case, let's first, so we'll do the uniaxial test for both, for all 3 cases, which is plane strain, plane stress, and 3D cases, the uniaxial type boundary condition. So displacement, I will fix this boundary condition, this edge in y2, in u2 or y direction, and then I will fix the vertical edge here with this one in u1 direction. And now these two are the free surfaces, so for uniaxial test or tension test, I can either pull in 2 direction, this edge to be in 2 direction and this edge in 1 direction. So in this case, I'm going to select this one and I will apply a u1 displacement of 1. So it will be, you will have 100% strain for that. And it's a ramp, so it will increase linearly with time. Now comes the point where you can first specify the mesh seeds. We give 0.1, it looks something like this, which is fine for this case. And then you select the element type. And here you have to select which element type you're going to go. So if it's a plane strain case, you will select the plane strain formulation. If it's a plane stress case, you will select the plane stress formulation. So let's start with plane strain. Remember, plane strain is the case where the strain in the Z direction, which is orthogonal to the screen, or the thickness direction, is 0 because your structure is so thick that it cannot feel any strain in the thickness direction, which is orthogonal to the screen current. So I will just do that, and then I will mesh it. So if I now query the mesh, then it should be saying that you have CPE, which is the plane strain, PE is the plane strain, and PS generally is plane stress. It's a reduced integration element. So once I have done that, I go to the job, then I will say create, and I will say plane strain case. Okay, I'll just keep everything default. Normally I go with the double full precision for all the outputs, then I submit. So if everything is fine, this should run in no time. So as you can see, it is running perfectly fine. And it finishes in less than a minute. Now if I go to the results, then you can see the results look something like this. And you have a large deformation. I think the stresses look very much the same. So what I can do now, I can go to tools, sorry, should be tools, XY data manager, create XY data, field output, and then I can select one of the elements. Maybe I will select one of the middle elements here, and this one. So this is the element we have selected, and then I will select the variables. So I need logarithmic strain in one direction and also the stress in one direction for that element. And I will save it. So I can save it as absolute values so that we don't need to use absolute again. And you can remember the element number here so that we will do the same for the other one as well, which is element number 55. And now I will operate on XY data, and I will combine the strain. Horizontal axis is strain and vertical axis stress. And I will say S versus E for plane strain case. So that's what I've done here. If I show you the plot, it looks something like this, which we expect that will go like this, and then there will be a horizontal line. So this is the case for plane strain, right? And if you look at other variables, so you will see that in the strain, L33 should be 0 because it's a plane strain case, while all the other strains should not be 0, as you can see here. Everything is there. Shear, there is a uniaxial loading, so obviously shear component is almost negligible. And same doesn't apply to stresses, because even though strains are 0, but it may not be the case, and stresses could not be 0. That's why it's called only plane strain case, because strains are 0, and generally this assumption is valid for very thick components. As you can see, all the others have finite values as compared to the strain LE33. So this is based on the plane strain case. Now if I want to run the same simulation with plane stress case, and what I have to do, I have to just go and change the formulation here, and in this case I will select plane stress. In this case, this will be plane stress for noded reduced integration elements. So once I have done that, I can double check if everything is working. It's doing fine, and you can see now it has changed to plane stress elements. Now I can go back and run the simulation. Plane stress cases are the cases where your structure out of plane thickness, which is in ZZ direction, is almost very small as compared to the other dimensions. So thin plates, thin structures where you will feel some lateral strain in that direction, you can assume plane stress cases rather than the plane strain case. And I will again create another job, and I will say plane stress. Continue. I will say full precision, and then submit. Most probably, let's see how the results look like. But as I showed you, plane strain case, your LE33 should be 0, and that is the thing which you have to keep in mind for plane strain case. For plane stress case, the stresses in 3 direction should be 0, and that's what we're going to check now. So let's go here. Firstly, the deformation, which looks very similar. Then I will go to the XY data manager, and I will say create field output. And if you remember, the element number I told you was 55. I think it should be somewhere in the middle, as you can see. So I will say LE11 and S11 as same as before, and I will go with the absolute value. And now I will do operate on XY data, combine LE, strain, and then stress, and then save. So gas V versus E, and now we will say plane stress case. So this is the plane stress case. Now if I plot, so now I have plotted plane strain versus plane stress, and you can see they show slightly different response. And in the case of plane, see which is worked, sorry. So blue one seems to be plane stress, and which is basically almost having the yielding occurring at same value as we have given us 350, while plane strain response is much stiffer, as you can see, and also yields much later than what you see for the plane strain case. It's just because of the thickness assumption and the strain to be 0. So this, the formulation assumption also So the assumption whether it's plane strain or plane stress case changes the response of the elements as well, although the constitutive model is the same. And it is just because of the fact that for the plane strain case, strain in 3-3 direction is 0, while in the plane stress case, the stress in the thickness direction or 3-3 direction is 0. Now let me show you the stresses. You see this is a mesos stress, and if I plot other components, S11 has a finite value, S22 has a finite value, S12 will have a finite value, which is small because it's not a shear loading, but S33 should be 0 because it's a plane stress case. But for the case of plane strain conditions in 3D, now I will show you how you can do that. And remember, for plane strain case, we got slightly, sorry, this is not the one. We got slightly stiffer response and late, and it yields at a higher stress value just because of the plane strain conditions due to the constraint or restrictions in the strain and thickness direction to be 0. Okay, so now let's go back and reconstruct the model in 3D and then do the same exercise. So I will say create new model, maybe create a new model, model 2, and this is model 2 now. So I will create a part. Now let's go to 3D and again start with 0, 0 and then 1, 1, and then I will give an out of plane thickness because it's an extrusion. Oops, sorry, I didn't select the proper one. So I'll delete this part and I'll start again. Create 3D solid extrusion, and then start from 0, 0 and then 1, 1, and then when I have done with this, I'll press done. And then I will give a depth also, or out of plane thickness, to be 1 as well. So you see now it looks something like this. In the previous case for plane strain and plane stress, we didn't model this edge or this dimension because we were modeling everything in XY plane, and based on the assumption that the geometry is either too thin, so we can assume it to be plane stress case, or it's too thick, so that we can assume it to be plane stress. So now property wise, again we can create a property. So elastic properties, same as before, 210,000 and 4.33, and elasticity 353 and no 350 I think it should be, and then 0.0, and then leave it as ideal, and then create a solid homogeneous section. We don't need any plane stress or strain thickness here because we used one before, so now it's done. Okay, so let's see what we can do with this. Just want to make sure that model 1 has the same properties. So if I go and press edit, it's 21,000 and 350. So now if I go back to model 2, then it should be 21,000 and 350. So it looks good. Okay, so now we move to the next one. Let's test part in the assembly module, and this is the part here. And next is we go to a SEM step, general step, same steps which we did, total time period of 1, maximum number of increments to be 10,000, initial increment size and maximum increment size equals to 1. Press OK. No interactions, loading. And now we will apply the same loading conditions as we did for the uniaxial case. So first I will define the uniaxial conditions as we did it for the previous 2-dimension or 2.5D case. So if you remember, this was the XY plane we pulled in this direction, so we need to fix this plane in that direction. Okay, bottom one, which is this one, in Y direction, which is U2. Again, going back here, and then this plane should be fixed in 3 direction. Sorry, in 1 direction, which is X direction. So this is what it looks like, and then these 2 surfaces should be free for uniaxial case, and we pulled it in 1 direction. So that's what I'm going to do now. Displacement boundary condition, and we will say U1, and in that case we give a displacement of 1 and ramp. So now if you simulate it like this, then these 2 surfaces are free, and what will happen as you pull it in this direction due to Poisson's effect, this edge and that other face will start to contract, Poisson's effect. But so let's run it like this, and then we will shift it towards the plane strain condition. So 0.1, same. I'm trying to use this, keep everything as similar as possible. You can query the mesh as well and see what it is. It's 3D8 are elements, 8 noded elements with reduced integration. Create, and now 3D uniaxial case. Okay. Full precision. Separate. Okay, so it's finished. Let's go to results and see how it looks like. So it looks very similar to what was. So basically we saw this kind of view, right? And now we have to really, but in this case it's a 3D, so we see this, and you can see that there is a contraction in this plane along this direction, which is Z direction, and also the other direction. This is a typical uniaxial case. So let me show you how the stress strain plot looks like for this. So what I can do is I can just select some of the elements or selecting the parts. So again, elements, pick from the viewport this, and then I will remove them first. I'll bring this side, and then I will select one of the elements from the middle. So let's query, or let's create field output, then same variables, but select the element which is somewhere here, and then save absolute values from here, edit, okay, variables, save, then I will select absolute, this is there. So again, this is element 555, remember that. Operate on XY data, combine strain versus stress, save 3, I think axial 3D. It will not let us start the name of the variable with the number, so I have to move 3D at the end. So now if I plot this, then this should look something like what we got for plane stress case as well. And if I can delete this, so this is how it looks like. So now if I plot all these things, so you see plane stress case and the uniaxial case are the same, because the stress is not stress is 0 because of the current boundary conditions we had, but strain is not 0. So you can see the uniaxial case may be similar to plane stress case if your structure is thin enough. But again, this is just a very vague statement. Now let's see what we can do to make a 3D simulation of plane strain case. So I will go back to the loading conditions here. And what I would do now, out of plane is the other face here. So I will fix that as well in Z direction. And this will make the stresses in this plane, in this Z direction, to be 0. So that's what I'm going to do here. Displacements, plane U1 to be 0. So now if I see, what I have done is basically there is no relative motion in this plane, in this axis, along this axis, which is Z axis, and there will be no contraction because of the loading condition we have put here. And hopefully that should do the trick for us. I hope I specified the right boundary condition. U1, no, it should be U3, sorry, because it should be fixed in the thickness direction. So sorry about that. It's having a long day today. So U3 is fixed for both these planes here and the other side as well. So there shouldn't be any lateral motion. So it's kind of a plane strain case, but still it can contract in this direction, which was the case of plane strain condition. Now if I go there, create 3D plane strain case, and that would be look something like this. Then if I submit, finish, so let's go results. So you see now it's the plane strain case. Displacement deformation looks similar, but you can see there is no lateral deformation here. which is the case for plane strain where there is no strain here. If I plot or look at the strain in 3 direction, then you will see it's almost 0 approximately because of the boundary condition. So it seems it's working fine. So first thing is what I'm going to, so it is plane strain case. Now let's see the stress strain response. Field output. And now I will say element label, F5 was it? I think highlight somewhere in the middle, save absolute values. Okay, and now create, operate on XY data, combine strain versus stress, save, and here I will call it plane strain 3D. Okay, that's done. And if I plot now, so what you see here is it is definitely yielding at a higher stress. So if I plot this with a plane strain case, they should be matching each other. So this way you can apply loading and boundary condition on your 3D structure to make it go or behave in a plane strain or plane stress case. So what we found out today was uniaxial case requires 2 surfaces to be free so that it can have that Poisson's effect, and plane stress condition can replicate that. So we found the plane stress results similar to uniaxial condition, boundary conditions. And similarly, to make a plane strain case in 3D, we need to fix the opposite face to the out of plane thickness direction so that there is no strain in the thickness direction, and that will make it a plane strain case. And you can see stress strain response become very similar for both the cases, whether you do it in 2D and 3D. Now coming back to the CPFEM, it's the same thing. You, instead of using the default model, you can use the UMAT and it should work in 3D. However, remember that your grains in polycrystalline material are not plane strain, because as you move along the thickness direction here, they are some irregular shape, so you cannot model them as plane strain. However, if you have an additively manufactured component where the grain growth is in this direction and you have a columnar grains which are very thick in this direction, you may assume or model it as plane strain case as well. So again, it depends on your microstructure, what you're modeling, and then you can decide which condition should be best for you to simulate. I hope this makes sense. Any questions, please comment below, and definitely forward and like the video. Otherwise, this video will die here, and I'm not getting much of the views these days. It's just because if people just view the recording and then don't like it or comment, then algorithm doesn't really promotes it. So thank you again, and good luck with everything. Any questions, get back to me. Bye for now.